So let's start off the first question of limits continued in differentiability, and the first question asks us to find the limit as n tends to infinity of box x plus box 2x plus so on till box nx whole divided by n square. So how do we solve this problem?
As we can see in the question, all the terms comprises of box x. Okay, so moving into the main property of box x, which is box x always lies from x to x minus 1. So we are going to be using this identity over in this question.
Okay, right. So is that an example which is below the identity?
Exactly. Like let us take x equals to 1.2. So box x will become 1.
Right.
Okay, and going back to this identity, we can see that 1 lies from 1.2 to 0.2.
Perfect. So how will you incorporate this identity in the question?
Okay, so when I substitute this equation, when I substitute this inequality into the question, we get this, but before that, let me take s equals to box x plus box of 2x, so on till box of nx divided by n square.
Okay.
Okay.
Right. Right. So yeah, how do we? Yes, this is the first assumption. This is the first thing we take. Okay.
Exactly.
So after that, we incorporate this inequality
into the question.
Right.
So we get s is less than or equals to x plus 2x and so on till nx divided by n square.
Right.
And is greater than or equals to x minus 1 plus 2x minus 1 so on till nx minus 1 divided by n square.
Right.
Okay, so now to simplify this, we'll use one property of sequence and series, that is sigma n equals to n times n plus 1 divided by 2.
Perfect.
Okay, and now when we apply this, before that we take x common from the given inequality we have got. Okay, so it will become s is less than or equals to x times n plus 1 whole divided by 2n square.
Yes.
And it is greater than or equals to n times n plus 1 x by 2 minus n whole divided by n square.
Perfect. And this identity has been used over here, and because we have taken common, and this minus n comes over here because there are minus n times minus 1 expressions are there in the numerator.
Exactly.
Perfect.
Okay.
So how do we move on?
Now since we have the inequality with us, we'll apply limit n tending to infinity all the sides.
All the sides. Perfect.
Okay. So when we apply this limit n tending to infinity and looking into the right hand side, we have n square in the highest degree is n square in the numerator as well as in the denominator.
Yes.
Okay. So for the next step, we'll divide by n square both numerator and denominator.
Right. So here n square gets cancelled, and here n square gets cancelled in the first term, and the second term becomes 1 by n.
Exactly.
Right.
So now we are left with limit s when n tends to infinity is less than equals to limit n tends to infinity x times 1 plus 1 by n whole divided by 2 and is greater than or equals to limit n tends to infinity 1 plus 1 by n into x by 2 minus 1 by n.
Similar deductions from as in the right hand limit will hold us in the left hand limit, right?
Very true.
Yes.
And now we know that limit n tends to infinity 1 by n equals to 0. So we use this concept and we get to the conclusion that limit n tends to infinity s is less than or equals to x by 2 as well as it's greater than or equals to x by 2.
Perfect.
Okay, so now we're looking into this expression, we can see that sandwich theorem will hold true in this one.
Okay, so I'm assuming this is sandwich theorem?
Exactly. Sandwich theorem states that when hx is less than fx, when which is less than gx, and if limit x tends to a, hx equals to limit x tends to a, gx equals to k, which is a finite value, then limit x tends to a, fx will also be equals to k.
Okay, right.
Okay, so now I'll apply this identity in this question and we'll prove, and now we can see that limit n tends to infinity of s equals to x by 2.
Right, perfect. So this is exactly what we needed, right? This was the question. So limit n tends to infinity of s is what we needed to find in the question, right?
Exactly.
Right, so let's just recapitulate the question over here. Question 1 was to find limit n tending to infinity of box x plus box 2x and so on till box nx whole divided by n square. So firstly we use this identity of box x by the definition of greatest integer function, and we incorporated that into this particular assumption we've made over here as s is equal to box x plus box 2x and so on till box nx by n square. So now basically what all we needed to do was find limit of n tending to infinity of s. So that's what we did. We used a couple of basic axioms which we knew from arithmetic, and we finally arrived at the answer as x by 2. So that is question number 1. Right, so the second question over here would be for us to find out the limit of n tending to infinity of n by n square plus 1 plus n by n square plus 2 plus so on and so forth till n by n square plus n. So right, so how do we start off with this?
Okay, so now when we look into the question, we can observe that the numerator is always the same, that is n, and looking into the denominator, it is n square plus 1, then n square plus 2, and so on till n square plus n.
Perfect.
So we see that there is an increment by 1 in the every next term
Of the
in the denominator.
Yes.
Okay, so now let us assume that the given expression, that is n upon n square plus 1 and so on till n upon n square plus n equals to L.
Okay.
Okay, so now we know that one thing, that if the denominator is minimum, then the sum will be maximum.
Yes.
Okay,
That's
so now what I'm going to do is that n square plus 1 is the lowest term amongst all the denominators. So I'm going to replace all the denominators by n square plus 1.
Right.
So we have minimized all the denominators. So the sum that we will be getting will be the maximum.
Yes, perfect.
Okay, so we get L is less than n times n upon n square plus 1.
Perfect.
Okay, so moving ahead, similarly applying the concept that denominator is maximum, the sum will be minimum.
Yes, indeed.
Okay, so what I am going to do next is I am going to replace all the denominators with n square plus n. Okay, so
Okay.
now L will become greater than n upon n square plus n upon n square plus n, so on.
Till n upon n square.
Exactly. So what will happen? L will be greater than n square upon n square plus n. Okay, so now we have this inequality with us. So I'm going to apply limit n tending to infinity all the sides.
Right.
Okay, so now moving ahead, we can see that the degree of n is 2 in both numerator and denominator, in both left hand side as well as right hand side.
Very true.
So what I'm going to do next is I'm going to divide it, the both numerator and denominator, by n square in both left hand side as well as right hand side.
Perfect.
So what we get is the next step is limit n tending to infinity L is less than limit n tending to infinity 1 upon 1 plus 1 by n square.
Yes.
And is greater than limit n tending to infinity 1 upon 1 plus 1 by n.
Yes. So as n tends to infinity, 1 by n tends to 0, right?
Exactly. Now I apply the limit and I get limit n tends to infinity L lies from 1 to 1.
Yes, perfect.
Okay, so now
So this reminds us of the sandwich theorem.
exactly, now we can see that sandwich theorem is applicable in this question also. So we can conclude that limit n tends to infinity L equals to 1.
Right. So this was exactly the question which was asked. So pretty much what we need to see is observe is that there's a particular flow to these kind of questions. The questions might look panicky. They might just scare you in the middle. But yeah, there is a particular flow, and sandwich theorem seems to be very helpful to us.
Exactly.
So finally, we come to an inequality where both the LHL and the RHL, the right hand and the left hand limits, are equal. So as soon as we apply the sandwich theorem, we get the answer as 1, and this was the answer for question number 2. So coming to the third question, this asks us to find the limit of 2x minus sine inverse x whole divided by 2x plus tan inverse x as x tends to 0. So looking at this question, if I substitute x as 0, 2x becomes 0, sine inverse x becomes 0, x becomes 0, tan inverse x also becomes 0. So it lies in a 0 by 0 format. So yeah, what can you just explain how we go through this problem?
We can see that it is a 0 by 0 format.
Right.
Okay, and we know that 2x, sine inverse x and tan inverse x are differentiable function at x equals to 0.
Yes.
Okay, so now I'm going to directly apply L'Hospital rule in this given question.
Okay.
Okay, so our question simplifies that limit x tends to 0, 2 minus 1 upon 1 plus 1 minus x square whole divided by 2 plus 1 plus x square.
Right.
Okay, so
this is what we this is basically we differentiated both the numerator and the denominator according to the L'Hospital rule, right?
exactly.
And these are the differentiations of sine inverse x and tan inverse x with respect to x.
Exactly, which
Right.
we must remember. Okay, so now since we have the format, and when we apply limit x tends to 0, it is not a 0 by 0 format and we get 1 by 3, we know that this is our answer.
Oh, so it's pretty simple. I mean, it's a 2-3 step problem. As soon as we know that it's a 0 by 0 format, we apply. We know the fact that we can apply the L'Hospital rule, and as soon as we apply the L'Hospital rule, one simple fact that we remember, the differentiation of sine inverse of x with respect to x and tan inverse of x with respect to x will immediately get us to the solution as to the limit being equal to 1 by 3. So yeah, just tell us if what if it was cot inverse of x or cosecant inverse of x instead of sine inverse and tan
Okay,
inverse.
so for all those things we can remember their formulas also, because it will come in handy in a lot of questions. Okay, so the main formulas are d by dx of cos inverse x equals to minus 1 upon 1 minus x square's root. D by dx of cot inverse x equals to minus 1 divided by 1 plus x square.
Right.
D by dx of sec inverse x equals to 1 divided by mod x into root of x square minus 1.
Right.
And d by dx of cosec inverse x equals to minus 1 upon mod x into root of x square minus 1.
Perfect. So these 6 formulae will come in very, very handy, because we have already seen that a question like this has been broken down into 3 steps as soon as we got the solution. So 1 by 3 is the required limit of question number 3. Right, so the fourth question over here is for us to find the limit of 1 per cosecant square x plus 2 per cosecant square x plus so on and so forth till n per cosecant square x whole power sine square x as x tends to 0. Right, so yeah, so how do we approach this problem? It's pretty scary, considering there are squares of trigonometric functions as powers, and there are different terms being added and you have to find the limit of it. So yeah, how do
looking into the question, we can see that all the terms are raised to the same power, that is cosec square x, and even sine square x is what? 1 upon cosec square x.
Exactly.
So to simplify is for our comfort, we'll take y equals to cosec square x. Okay, and we must always remember one thing: whenever we are using substitution, we should also simultaneously change the limits accordingly. So when x was tending to 0, cosec square x was tending to infinity.
Right.
So our y will be tending to infinity now.
Exactly.
Okay, so applying these changes in the question, we are left with limit y tends to infinity, 1 raised to y plus 2 raised to y, so on till n raised to y, whole raised to 1 by y.
Yes, perfect.
Okay, so now we can see that when we apply the limit, this question becomes infinity raised to 0 format.
Exactly.
It's an indeterminate format.
True.
Okay, so now moving into the next step, so we'll take n outside the bracket. Okay, so it becomes limit y tends to infinity, n raised to y whole raised to 1 by y into 1 by n raised to y plus 2 by n raised to y, so on till n by n raised to y whole raised to 1 by y.
Okay.
So now our next step becomes limit y tends to infinity n times 1 by n raised to y, so on till 1 raised to y whole raised to 1 by y. So now there is one important concept that I want you guys to remember. 1 raised to infinity is an indeterminate form only when it is a tending one. It's not an exact one.
Okay.
When we know that it's exact one and it's raised to infinity, it will be 1, because it's 1 into 1 into 1, which will definitely give us 1.
Right. Makes sense.
Okay, so now we know that the above question had 1 raised to y, that was an exact one. So we know that that value will be equals to 1.
Yes.
Okay, and now I want you to look into this expression, which is a raised to infinity. When a lies from 0 to 1, we know that it will be 0.
Yes, of course.
Okay, because it's fraction multiplied by fractions, which will infinite times, that will give us 0.
Right.
And when a is exactly 1, we know it will be equals to 1. And when a is greater than 1, it will be tending to infinity.
Right, perfect.
Okay, so now I'll want you guys to use this concept in the question. So it will become limit y tends to infinity n times 0 plus 0 and so on till 1 raised to 1 by y.
Perfect.
Okay, so this will become limits y tends to infinity n times 1 raised to 1 by y. But since we know that it's an exact one, this question answer become n equals to n.
Perfect. So that's pretty simple again, isn't it? So the final answer of let's just recap for a second over here. So there's a limit. There were complicated addition terms and trigonometric squares and whatnot. But once we see the similarity of cosecant square x being a very common term, and also sine square x, which can be expressed in terms of cosecant square x, we immediately took up y equals cosecant square x. And we change the limits accordingly. X tends to 0 means that cosecant square x tends to infinity, which also means that y tends to infinity. So deducing those, and also using a couple of facts that a couple of functions, for example, like a power infinity, having different values at different values for a, we immediately found out the answer as n. So that's pretty simple, isn't it?
Exactly.
Right, so this is answer n for the question number 4. Right, so question number 5, we have find points of discontinuity of y is equal to 1 by u square plus u minus 2, where u is equal to 1 by x minus 1. Right, so we have a function where we have a quadratic denominator, and we have u as also a fraction. So how do we go about this?
As we can see that we have a composite function over here in the format of f of gx. Okay,
right.
So we can see that gx, which is u over here, equals to 1 upon x minus 1, whereas f of gx is y, which is equals to 1 upon u square plus u minus 2.
Right.
Okay, so now moving into the next step, we know that f of gx will be discontinuous at the points where gx won't be continuous.
Yes, exactly.
Okay,
so that means u cannot exist, as that's where the points of discontinuity exist.
Exactly. So u will be discontinuous when its denominator will be 0,
yes,
which is x equals to 1. And so since x equals to 1, u won't be defined, so we know that f of gx, which is y, won't be defined. So here we get the first point of discontinuity.
Exactly. So x is equal to 1 is the first point of discontinuity. Okay, so how do you find out more points of discontinuity?
Now going back to the f of gx, which is y equals to 1 upon u square plus u minus 2. Okay, so just for a simplification, we'll factorize the denominator, and we get y equals to 1 upon u plus 2 into u minus 1.
Right.
Applying the same logic over here again, y will be discontinuous where its denominator is 0. So going by it, when u equals to minus 2 and u equals to 1, our denominator gets 0. So at these points, f of gx will be discontinuous.
Exactly. Okay.
Okay, so finding out the corresponding values of x for these values of u, we get x equals to 1 by 2 for u equals to minus 2, and x equals to 2 for u equals to 1.
Right. So basically, as soon as you find out that the points of discontinuity lie when u is equal to minus 2 and u is equal to 1, we try to calculate the corresponding x's of those particular values of u. So the first point of discontinuity, the second point of discontinuity after we found out that x equals 1 is already a point of discontinuity, would be x is equal to half, while the third point of discontinuity would be x equal to 3.
Exactly.
Right. So this is a pretty straightforward question as such, I believe, and so we found out 3 points of discontinuity, and there were 1, half, and 2. So that's question number 5. Right, so the sixth question we have here is that f of x is equal to maximum of sine t, where t lies between x and 0, whereas x lies between 0 and 2 pi. Discuss continuity of the function at x is equal to pi by 2. Right, so I believe for questions like these we need to plot down the graph first.
Exactly. Whenever we are given with functions where we have to find max or minimum value, the basic steps should be always start with the plotting the graph of the inner function that we have been given, which is sin t over here.
Right. So after we plot the graph, we notice that at x is equal to pi by 2, and in this case t is equal to pi by 2. Yeah, let me just write down that this is t and this is sin t, right?
Exactly.
So as when t is pi by 2, the value of sin t would be 1, and when t is pi, value of sin t will be 0, as everyone knows, right? So what do we get out of this, and how do we find out whether the function is continuous at x equals pi by 2?
Okay, now first I want you guys to understand this question. So t lies from 0 to x. Okay, so as we move x from 0 to pi by 2, value of t will also move from 0 to pi by 2.
Yes, of course.
Okay, so sin t value will lies from 0 to 1.
Yes.
So
indeed.
as we grow from 0 to pi by 2, the value of sin t will be constantly increasing. So max of sin t will be always be equal to sin t.
True. Yes, this is very true. Yes.
Okay, so since from x, when x lies from 0 to pi by 2, max of sin t will be equals to sin t.
Yes.
Okay, now at x equals to pi by 2, sin t attains its maximum, which is equals to 1. And beyond pi by 2 till 2 pi, it will always be less than 1.
Yes, of course.
Okay, so when we go from pi by 2 to 2 pi, max of sin t from when t lies from 0 to 2 pi will always be equals to 1.
Yes.
Okay, so we get the function over here. When x lies from 0 to pi by t, we get fx equals to sin x, and when x lies from pi by 2 to 2 pi, we get fx equals to 1.
Right. So this is the function which we got out of the equations, which out of the graph which we got out, and out of the we figured out that this was the equation which we got. So do we need to plot out another
exactly
graph?
By plotting out this graph we can actually, because we have to find out the continuity of the function. So
right, exactly. So the main point is that we find out the continuity of the function by plotting graphs, right?
Exactly.
Right.
And to plot graphs we need the function, and to get the function we need to simplify the function that has been given to us.
Okay, right. So at the end of the day, we figure out that when t is equal to pi by 2, sin t in fact is equal to 1, and it continues, and it's not a discontinuous point at all.
Exactly.
Right.
So we can conclude that the given function is continuous at x equals to pi by 2.
Continuous at t equals pi by 2.
Very true.
Yes. So this was question number 6.